Hello everyone. So this is a presentation on the Qfold software that we created for the RNA secondary structure prediction problem. This is a joint work with Dr. Lewis and Dr. Eckdahl from biology department. And in this presentation, I'm going to talk about some of the details of this software. And I encourage you to ask me any questions that you have. You can reach out to me via email and send me a message. Alright, so let's briefly discuss what the RNA secondary structure prediction problem entails. So we are given a sequence of nucleotides. These nucleotides are the bases A, C, G and U. For example, if you look at the figure on the left, this is the primary structure that is provided as an input. So you see a sequence of these bases C, G, C, A, U, C, A, U, and so on. And then we are also given interaction weights between pairs. I will discuss these later on in the slides. So this is just telling you that what is the energy associated with the pair A and T, or A and U, or C and G, and these are called the Watson-Crick base pairs. So there are some set rules for base pairing that we are going to use. So we are going to allow that A pairs with T, A pairs with U, and C pairs with G. This is a very fundamental problem in biology, and they have set of rules that determine how the secondary structure will look like. So in the biology world, the bases tend to pair with each other, and these are the pairing possibilities that are possible. Okay, so if you look at this figure here, you will see that A has paired with U, C has paired with G, and here G has paired with C, and so on. So these are the possibilities that exist with respect to the pairing of these bases. So again, to start, we are given the primary structure, which is nothing but a sequence of bases, and our task is to predict how the secondary structure or this figure in left will look like. This problem is not deterministic, because depending on the set of conditions like temperature, the pH value, the secondary structure might be different. So there are benchmark softwares available for this process, like Vienna RNA, and we are presenting a new modeling approach which will provide the software called Qfold. Alright, so let's discuss a little bit more about some of the parameters that are involved in this process. The secondary structure will be formed such that the minimum free energy is minimized. So if you look at this secondary structure, it will have associated minimum free energy tied to it, and the structure would like to be in a state of the lowest free energy, and that is what governs how the folding will happen. So usually the end result of this folding would determine a secondary structure which is at the lowest free energy state, and that will correspond to a stable RNA secondary structure. Also, there are some constraints which says that bases less than that minimum distance threshold of 4 units cannot pair with each other. So here you see that in this example, for instance, 10 cannot pair with 11, 12 cannot pair with 13 because they are too close. Also, there are two versions of this folding softwares out there. One which considers crossing base pairs, pseudoknots. So here, for instance, you would see that one of these pair between 8 and 12 crosses 4 and 18. So that's your crossing base pair. When you allow crossing base pairs, the problem becomes more complicated. So typically, most of the softwares that exist in the market, they will allow for non-crossing base pairs, and that is what we are going to assume also. So we are going to look at these non-crossing base pairs only in the RNA secondary structures. All right, this is how the folded structure looks like, and sometimes it's possible to figure out what that exact folding is through X-ray crystallography techniques, but these are expensive, and that is the reason most of the secondary structure prediction is done using softwares, because these secondary structure tend to have the lowest free energy parameters, and those are like, again, difficult to obtain what that state will look like, but again, it's possible using these softwares and some of these optimization techniques. So these are some of the features of the folded structure, the RNA folding. There are some hairpins which look like this, helix structure, and here you will always see that A pairs with U, G pairs with C. This is about, and there's some internal loops, and then this is that crossing base pair, pseudoknot. So these are the structural features of the folded RNA secondary structure. These are the free energies that I was referring to. So if you see what this table tells you, these are obtained from Turner 2009. These are also called Turner free energies. So if you look at this table, it will tell you that if AU is stacked on top of AU, that means A pairs with U, and then on top of it A pairs with U, then the energy state, energy value that is tied with that is 0.9. Remember, thermodynamics will guide us in determining these free energy states. Usually the molecules would like to be in the lowest free energy state, or the minimum free energy MFE states. So let's talk a little bit about the model. This is how our model looks like, and this is different from the benchmarks softwares that are there in the market. There is a very popular RNA folding software called Vienna RNA. There's Qfold, and then there are other softwares like that. But our model is based on quadratic unconstrained binary optimization, or QUBO, and it uses binary variables, and in our case the variables are, if a A pairs with a U, then we'll set that to 1, otherwise it will be set to 0. So this is based on the linear diagonal terms and quadratic off diagonal terms. We will tend to minimize the free energy state, and these are some of the constraints that will be tied to the model. So a base can only pair with one other base. A crossing pair is not allowed, that is pseudoknot is not allowed. There's a minimum distance constraint, that means nucleotides which are less than 4 nucleotides apart, they cannot pair with each other. And then we have a maximum distance constraint too. maximum is 200 nucleotides. We will see that as the number of nucleotides increases, this problem becomes really difficult. Alright, so let's figure out how this QUBO modeling paradigm works. It's reliant on this Q matrix, and this is how the Q matrix looks like. Q matrix is a way of determining or providing the solver what are the penalties or what are the incentives. So here, if you look at our binary variables, A at position 1 is paired with U at position 5, and C at position 2 is paired with G at position 4. So that kind of is a feasible alternative for us, and that's a good alternative. This is a possible alternative, so that's why we will reward 5 units. And again, these penalties are determined on the Turner free energies. So here, this is a preferred configuration that the solver will acknowledge, because these green values are the positive rewards, and then the reds are the negative penalties. So in this way, we will construct the Q matrix, and we have a solver which will take the Q matrix and figure out what is the best possible solution in that limited time frame. So in this way, we are able to determine which bases pair with which other base pair. Remember, this is our framework. So xi pairs with xj, and xi plus 1 pairs with xj minus 1. So that is just telling you that bases at different positions pair with bases at other positions, and that is here. If you look at this, A at position 1 pairs with U at position 5, and then C at position 2 pairs with G at position 4. So that is how we have defined our binary variables. So this is how the Qfold software that relies on the quadratic unconstrained binary optimization works. It takes as input a RNA sequence, and as output it provides secondary structures. Again, the objective is to minimize the free energy state, and here, for instance, if you look at the solution obtained by our solver, it starts at this state, maybe of a higher energy, because there are not many pairings in this state, and it eventually reaches this state with a lot of pairing and hairpin lobes and bulges. So that corresponds to a low free energy. So again, the transition is from a high free energy state to a low free energy state, because that is the objective of the optimization model. By the way, this is the benchmark that's typically used in RNA folding, the VNA RNA services, and we will compare our results with their in the upcoming slides. So again, this is how the solution progression will look like. Remember, our target is the state with the lowest free energy. So we typically start with something like this, where there are no pairs. Again, if there are no pairs, there are no options to obtain low free energy. It's a very unstable state. So eventually you see these pairs at the end, and again you see like G pairing with C, A pairing with U, and so on. So the progression is towards the lowest free energy state, which will look something like this. This is the behavior of the solution, and the problem size as the number of nucleotides increases. So as the sequence length, RNA sequence length, the primary sequence length increases, these problems become very difficult, and the Q matrix that we constructed, the size of the Q matrix also increases rapidly as the RNA length increases. So we are looking at these difficult problems as we move from like 200 nucleotides to like 300, 400, 500 nucleotides. We compared the results that we obtained across a wide variety of benchmark. Again, these benchmark problems can be obtained from the Vienna RNA services. This is how we perform with respect to the benchmark. F score is one of the measures that we used. F score is like how good is your prediction with respect to the benchmark. So 1 means it's absolutely good, it's the best you can achieve. So here we as the number of nucleotides increases, as the RNA length increases, the performance somewhat like reduces, but still we are hitting that level of 0.8, 0.7, 0.6. So that's a pretty good prediction measure for our Qfold software. And we also have this measure called MCC, which combines like true positives, false positives, true negatives, and false negatives. So as again, this measure even for Vienna RNA is towards a lower spectrum, like around 0.5, and ours again, as the RNA length increases, the performance diminishes, but still we are consistently like hitting like 0.5, which is typically what Vienna RNA achieves for these longer nucleotides. These are some other measures of performance, precision, and recall, and again we are hitting that consistent benchmark like of 80%. But again, one thing that I want to say is as the RNA length increases, the performance of our software diminishes, and it's also true with the other benchmark softwares out there like Vienna RNA, Qfold, and other softwares. Because remember, these problems are becoming more and more difficult as the problem size is increasing. We also did some sensitivity analysis and trying to see what happens when we change some of these parameters or some of these assumptions that we made earlier, like for example the distance, minimum distance of 4 nucleotides. What happens when we change it to 3 nucleotides? Again, some instances the solution didn't change, but it changed drastically for some other instances. So it just depends on the type of RNA primary structure and what are the different possibilities with the pairing. So here you see that the distance is 4 nucleotides, and you can see that that's satisfied here, but here you would see that the distance between the pairs is at least 3 nucleotides. So that is the sensitivity results with respect to the minimum distance parameter. And this was the comparison that I was referring to earlier. We compared our software results with Vienna RNA, and these are some of the comparison results. And you would see that this is our Qfold software. Again, this is using the Turner weights. This is the morphology that we obtained. This is the secondary structure that we obtained, and this is the one that's obtained by Vienna RNA. And as I said earlier, this problem is not deterministic. That means that there's not one best solution, because it just depends on the temperature, the pH value, and it's very hard to determine how exactly the RNA primary structure will fold. So that's why We are interested in finding these solutions, and these solutions can provide tools to the people working in RNA folding, and it's very important. It's a very important problem. That's a very well studied problem. By the way, if we change the Turner weights to the Kelly weights in the literature, this is what we get. This is the structure that we obtained using the software, and then these are the X-ray crystallography results that are verified in the lab. And you would see that there are some pseudo knots here. So this was the comparison of our software with different parameter choices and the benchmark, which is the VNA RNA services. Alright, so with this I would like to end my presentation, and again my name is Dr. Amit Verma. My office is in the Popplewell building. Please reach out to me in case you have any questions regarding the software, or you would like to use the software in your course. So yeah, thanks a lot for your time, and I wish you all the best, and take care and stay safe. Thank you.